Let's begin with lesson 1, solving systems using tables and graph. As we're going through here, I will be writing my answers in just like you would. If you would like to follow along, we'll do that. So let's look first. We know that Unit 4 is all about systems. So let's look at some definitions. So when you have two or more related unknowns, so this is basically saying when you have two or more variables, you may be able to represent their relationship with a system of equations. I'm just going to abbreviate equations there since it won't fit in the blank. And a system of equations is two or more equations. We're going to focus mainly right now on two equations, but later in the course, we'll deal with three. So you may see that. Okay. A linear system consists of linear equations. So just to recap, what does linear mean? Well, obviously it means there's a line involved if you were to graph them, but if you're looking at the equations, this just means you're going to have no exponents and no division of variables. That means that the variables can't be in the denominator. So we'll just add a little bit extra there with the notes. Okay. And then a blank is a system of values for the variables. So this is a solution. A solution is a system of values for the variable that makes the equations true. So we have some good language here. You'll want to know what the language means as we move forward because it's going to help you know what the question's asking. It's going to help you know, like, what do I do with these equations? Now, at the bottom of this page, you're going to see what I think is such an awesome diagram. And I see a little note over here that tells me, hey, this piece of information will be very helpful on the test question number 8. So I'm going to kind of highlight that in my notes. I don't know about you, but I like to use color when I do math because research shows us that your eye will come back to, oh yeah, it was in yellow on the page and you'll remember it. So use color any chance you can. So let's look at this diagram. It tells us that when we have a linear system, remember a system is two or more equations. A linear system is where they make lines, right? Both of the equations are lines. We have one of three scenarios. So the first scenario, and I'm going to give it a color too. The first scenario is where they intersect. The lines obviously intersect, and they intersect right there. That means we're going to have one solution. Now here's some other words that you might see associated with this type. It's consistent, it's dependent. All right, then we might have coinciding lines. This is where the two lines actually land in the exact same place. And when this happens, let me get a better color. When this happens, we have infinitely many solutions. Okay, again, you might see the words consistent and dependent used for that. Just so you know, I never remember consistent and dependent, but I have them in my notes so that I know where to go if I need to find that out. And then finally, we have where the two lines end up being parallel. And when that happens, we have no solution. And no solution, we can also use the word inconsistent for that system of equations. So you can tell I'm very into my colors. But let's keep going because we've got some good language going on here. We just want to know how to use it. So let's start with doing some good old graphing. Good old graphing. I love to graph lines. Oh, and I see another one of those little boxes there that's supposed to remind me, hey, this helps with test question number 1. I definitely want to make note of that. There we go. Okay, so let's see if we can graph these two lines and let's see where they intersect. So remember, to graph a line, we generally, it's pretty easy to use y equals mx plus b. So I'm going to take the first equation, negative 3x plus 2y equals 8. And I'm going to get the y by itself so that I can see what the m is and what the b is. So to get y by itself, I'm going to add the 3x to both sides. Now you'll notice that I did not line that 3x right up underneath the 8. The reason I didn't do that is because I don't like terms. So I wrote it to the side, and you're going to notice I actually like my x's to come first. So when I write this, I have 3x plus 8. See, I like the x's to come first, so I just flip-flopped them. Remember, order doesn't matter when we add. You may be thinking to yourself, well, why didn't you write this down here? Well, look what we have, negative 3x plus 3x. Those cancel. So I'm going to mark those off. Okay, one last step to get y by itself. So I'm going to divide each term by 2. And I do it each term because I want to make sure I divide each thing by 2. So 2 divided by 2 will give me 1y. And then watch how I'm going to write this 3x divided by 2. I'm going to write that as 3 halves times x. Now think to yourself, where did she get the 3 halves? Look at where it was, and I just moved it in front of the x. The reason I did that is because I need to know what m is, and m is the number in front of x. So very easy, I wanted that m there. Okay, and then plus 8 divided by 2 is 4. Lovely, got a great equation now. It's in slope-intercept form. We call that mx plus b. So m here is 3 halves, and b here is 4. Now b tells me where to start on the y-axis. So I'm going to go up to 4, 2, 3, 4. I'm going to put a dot there. And then I'm going to use my slope, which is 3 halves. Remember, rise over run. So that means from here, I'm going up 3, 3, run 2, 1, 2, put a dot. Do it one more time. Up 3, right 2, voila. There we go. I'm going to use just a straight edge, a little notepad here. I like my lines to be straight. I don't know about you. I'm going to put arrows on the end, show that it goes infinitely in both directions. All right. Now we're going to do the exact same thing for the other equation. So I'm going to have x plus 2y equals negative 8. And I'm going to get the y by itself. So again, same process, right? I'm still going to subtract this x. I'm not going to put it underneath the negative 8 because they're not like terms. Remember, this language is similar because I'm doing the same thing. Okay, and so that leaves me with 2y equals, remember, I like my x's to come first. All right, and then I'm going to divide by 2. Remember how I do it? I divide each term by 2. So that gives me y equals negative 1/2 x minus 4. So I went a little bit faster on that one because I kind of talked through it over here on the first one. Look at how I wrote that negative 1/2 x because I want you to think about if you divide by 2, that's the same thing as multiplying by 1/2. But I need to write it like this. I can tell you easily that m is negative 1/2 and b is negative 4. Okay, where do we start? We start with the b. So we go on the y-axis, we put b as negative 4. And now we're going with the negative slope. So remember, negative slope means to go down and right or up and left. I like down and right, kind of makes me feel a little bit better. So down 1, right 2. Do it again, down 1, right 2. I just like to draw a stronger line. That's why I do 3 points there. I'm going to try to line it up really good here. There we go. And I didn't even draw a really good line, did I? So let's do up 1, left 2, up 1, left 2. There's where I would get a better line. So we see that the two lines intersect at this point right here. If I had drawn my line better, it would be a little bit better. Let me see if I can draw it a little bit better. I'm gonna have to come over here to get to be able to do that. Where it goes through all the points, there we go. All right, now what are the coordinates for that point? Well, they're -4, -2. So that means that's my solution. It's a lot of work, isn't it, for graphing? It's not that graphing doesn't work. We just look at all the tools we had to bring. One, we have to solve the equations. Two, we have to have graph paper, right? So I want you to be able to do it. Obviously, test question number 1 is going to work on that, but I definitely want to look at some other methods as well. Okay, so let's go to some definitions then. So a consistent system has at least one solution. That means obviously that an inconsistent system has no solution. Okay, so now an independent system has one solution, and a dependent system I don't know that I spelled that right. I didn't. Let's spell it right. Dependent. A dependent system has infinitely many solutions. So we want to know, how would we classify this one? Well, I like this one. I want to try to see if they can look alike. Because if I can look and see if they look alike, it kind of helps me a little bit. So I'm going to try to make this second equation look like the first one. Some things I notice about the first one is that all of the variables are on the left side of the equation. So I'm going to try to make the second equation look like the first one by moving the variables all to the left. So I'm going to take this equation and I'm going to move the 4x to the left by subtracting it. Now, I told you I like my x's to come first, but I noticed that my first equation has my y's coming first. So I'm actually going to leave the y's first in this one. You may be asking yourself, why didn't she subtract 8y minus 4x? I did. I can't subtract the 8 and the 4 because they're not like terms, right? Remember, they have to have the same variable, same exponents. So this is pretty much what I can do. All right, now let me just do a little bit. Now here's equation 1, and here's equation 2. So I noticed that these numbers look very similar. And so what I'm going to do, I'm going to take the first equation and I'm going to multiply by 2 just to see what happens. So I'm going to multiply every term in the first equation by 2. That's going to give me 8y minus 4x equals 12. The second equation, I'm not going to multiply at all. So this gives me 8y minus 4x equals negative 12. Ooh, those look really close, don't they? But they're not. There's a distinct difference. And because there's a difference, that means that when one side's exactly the same, but the other side is not the same, this is an inconsistent system. If they had been exactly the same on the left and exactly the same on the right, we would have gotten a dependent system. Right, a dependent system. So this is an inconsistent system here. Okay, let's take a look at two more problems. Actually, I'm going to do a problem for number 3. I'm going to do number 3 here, and then I'll make a separate video just for number 4. Let's take a look at number 3 here. We're going to have to use the graphing method. Here's why. I noticed that the graphing method, they gave me graphs. So there's a couple of things that I can do. Let's look at the answer choices first, okay? When you look at answer choice A, I want you to focus your attention on where the two lines intersect. Where they intersect tells us the solution, and in this case, the coordinates for the solution are 1, -3. Now, we can go to the equations and see if this works. Remember, a solution must make both equations true. So I'm going to take 4x plus y equals 1. I'm going to plug in 1 and -3, and let's see if we get the same on both sides. So 1 for x and -3 for y. So that's 4 plus -3 is 1. That one works, but it's not enough that it works in one equation. It's got to work in both equations. So let's check the other one. X plus 4y equals -11. Let's put in the same value. So I'm putting 1 for x and -3 for y. So 1 plus -2 equals -11. And that is -11 equals -11. Voila, it works in both equations. That tells me then that graph A must be the answer here, must be the graph for this system. We can go on and check the other graphs if you would like, but we don't really have to. We would do them the same way. We pick out the solution, we go plug them into both equations to see if they would get a true statement on both sides. So I hope that helps for lesson 1.